I have a question for you.
Okay.
When was the last time you felt that specific panic? You know, the one where your laptop freezes or the power flickers and you just realize you haven't hit save?
Oh, yeah, the Ctrl-S panic. It's a universal feeling.
It is. We live our lives around that fear. I mean, we constantly save, we plug in our chargers, carry backup
Yeah.
batteries. We treat our computers like they're incredibly fragile because, well, they are. Specifically, their memory is fragile.
It really is. We assume computers are these, steel traps of logic. But the actual component that holds your active thoughts, the RAM, is incredibly forgetful.
It forgets everything the moment the power cuts out.
Instantly.
But what if it didn't? What if your computer's short-term memory was just as permanent as its long-term storage? I mean, a world where you could unplug your desktop in the middle of a game, throw it in a moving truck, plug it in a week later, and just pick up exactly where you left off.
That is the dream of non-volatile computing.
Yeah.
And, typically it's just a dream. But a new paper came across my desk recently that suggests we might be getting a lot closer to reality.
Welcome to the Deep Dive Lab. Today we are unpacking a major breakthrough in semiconductor technology. We're talking about a new type of memory that holds data for hours, maybe even days, without power and without the massive energy drain of current tech.
It's a fascinating study. It was published just recently, January 14th, 2026, in Nature Materials.
Okay.
The title is a bit of a mouthful. It's Quasi-non-volatile capacitorless DRAM based on ultra-low-leakage edge contact MoS₂ transistors.
I'm glad you're the one reading that title.
Yeah, but it basically means they built a better memory chip using some very clever physics.
Right.
The work comes from a team at Fudan University in Shanghai.
Right.
The lead authors are Saifei Gu, Yukuzon Zhu, and Zijie Zhang, working with corresponding authors Shiyu Chen, Peng Zhu, and Wenzhong Bao.
So before we get into the quasi-non-volatile part, which I definitely want to ask about, we need to understand why my current computer is so bad at remembering things. Like, why does my battery drain so fast just leaving a browser tab open?
It all comes down to the architecture of DRAM. That's dynamic random access memory. For decades, the industry standard has been something called 1T1C.
1T1C. Okay, break that down for me.
One transistor, one capacitor.
Okay. I love a good analogy. How should I, picture this?
Think of the capacitor as a bucket. Its job is to hold electrons.
Okay.
If the bucket is full of electrons, the computer reads that as a 1. If it's empty, it's a 0. That's your data.
Simple enough. Bucket full, bucket empty.
Then you have the transistor. Think of that as the tap or the valve. It opens to fill the bucket, and it closes to keep the water inside.
Right, so if I have a bucket and a tap, where's the problem? Why is my battery dying?
Because the bucket has a hole in it,
Oh.
and the tap drips.
Wait, really? We've been building computers for 50 years and we haven't figured out how to patch the hole.
It's not a manufacturing defect. It's a physics problem. In silicon chips, the transistor is never perfectly closed.
Right.
We deal with something called sub-threshold leakage. So electrons sneak through even when the valve is supposed to be shut. And the capacitor itself leaks charge.
So my 1 is slowly draining away into a 0.
And slowly is a relative term here. We're talking milliseconds.
Wow.
So to keep your data from vanishing, the computer has to constantly check the bucket. It looks inside, sees it's getting low, and tops it off. It does this thousands of times per second.
That sounds exhausting.
It's called the refresh rate. It's like trying to keep a tire inflated that have a puncture, so you have to run an air pump 24/7.
Yeah.
That pump eats up a huge amount of your battery life.
And I'm guessing this gets harder as we try to make chips smaller. We always hear about Moore's law and things getting tinier.
Exactly. As you shrink the transistors, the walls get thinner. You start running into quantum tunneling.
Quantum tunneling? That sounds like something straight out of Ant-Man.
It essentially is. When barriers get that thin, electrons can just, they can teleport through them.
No way.
They don't go over the wall, they go through it. So the leakage gets worse, the buckets get leakier, and we're hitting a physical wall with silicon. We just can't make the seal tight enough.
So if silicon is failing us, I guess we need a new material. Enter the star of today's paper, MoS₂.
Molybdenum disulfide.
It sounds like a heavy metal band, but I know it's a semiconductor. What makes it better than silicon?
With 2D material. So imagine silicon as a big box of Legos. It's 3D. MoS₂, in this case, is a single sheet of atoms.
Like a sheet of paper versus a stack of books?
Even thinner, atomically thin. And this gives you incredible control over the flow of electricity. But the real advantage here is the surface. Silicon has what we call dangling bonds.
Dangling bonds.
Picture the surface of a Lego brick. It has a stud sticking up, right? They want to snap onto something. Silicon atoms on the surface are like that. They're looking for partners.
Mm-hmm.
And those dangling bonds grab onto impurities, they create defects. Those defects are where the leaks happen.
So silicon is naturally sticky or rough at the atomic level,
Right.
and that causes the leaks.
Precisely. MoS₂, on the other hand, is dangling Don-free. It's
Oh.
chemically self-contained. The surface is smooth and doesn't have those hooks. So in theory, it should seal perfectly.
In theory. But I'm guessing there's a catch, otherwise my iPhone would already be made of this.
The catch is connecting it to the rest of the world. You have this perfect, delicate atomic sheet.
Yeah.
And you need to attach a big, clunky metal wire to it.
The interface problem.
Right. The traditional method is called top contact. You just deposit the metal electrode right on top of the sheet.
Which sounds logical.
It seems logical, but remember, the MoS₂ doesn't have those hooks to grab the metal, so the metal just kind of sits there. It creates a gap, a van der Waals gap. It's like trying to stick Scotch tape onto a greasy surface. It doesn't stick well, and electricity has a hard time jumping across that gap.
So you have a great material, but a bad connection.
And that connection is where the resistance and the leakage happen. So this Fudan University team, they tried something different. Instead of putting the metal on top, they used edge contacts.
They went in from the side?
Yes. They connect the metal directly to the raw edge of the MoS₂ sheet. It's like stitching the wire directly into the weave of the fabric, rather than just laying it on top.
Okay, that makes sense geometrically. But reading the paper, the way they actually did this, it
Right.
sounded incredibly difficult. They used a custom vacuum chamber.
This is the engineering triumph of the paper. You can't just cut the material and then carry it across the room to put the metal on.
Why not?
Oxygen. The second you cut that MoS₂ sheet to expose the edge, it's vulnerable. If you do that in a normal room, oxygen atoms will instantly snap onto that fresh edge. That creates oxidation, basically rust, and it ruins the connection.
So it's like open heart surgery. You can't let any germs in.
Exactly. So they built a system to do everything in situ in place. Imagine a single machine where they can etch the material, clean it, and deposit the metal, all without ever breaking the vacuum seal.
They mentioned a soft plasma treatment in there too. What was that?
That's the cleaning step. Etching leaves the edge a bit ragged. The soft plasma it polishes it down gently. So you get a pristine, atomically clean interface between the semiconductor and the metal.
And because they kept it so clean, the results were, well, frankly, they were ridiculous. Let's talk about the leakage current.
This is the number that really matters. They measured a leakage of 1.75 times 10 to the power of negative 20 amps per micrometer.
That number is so small I can't even visualize it.
It's practically zero. It is effectively nothing.
Wow.
To put it in context, it's 2 orders of magnitude lower. That's 100 times better than the best top contact versions.
Okay, but why? I get that the seal is clean, but why is the edge contact so much better at stopping leaks than the top contact? The paper started talking about the Sommerfeld factor and dimensionality, and I got a little lost.
This is where the physics gets really, really cool. It's all about how electrons move through space.
Okay, walk me through this.
In a top contact scenario, the connection is essentially 3D. The electrons have a lot of room to move around.
Okay.
Imagine you're running through a wide open field. But the field is full of traps. These are the defects that cause leaks.
So I'm running through a field of landmines.
Exactly. And because it's a 3D space, you can approach a mine from any direction. The pull of those traps, the Coulombic attraction, is strong because there are so many ways to get scattered. The electrons get distracted, they bounce around, eventually they get caught.
So chaos.
It's chaos.
Right.
Now look at the edge contact. Because the MoS₂ is so thin and the connection is at the side, the physics shifts to 1D. It's no longer an open field, it's a narrow tunnel.
So I'm not in a field anymore, I'm in a hallway.
A very, very narrow hallway. And this creates what we call quantum confinement. The electrons are forced into a single file line.
Like stormtroopers marching down a corridor.
Better aim, hopefully. But yes,
Yeah.
because they are confined to this 1D path, the Sommerfeld factor, which basically describes how likely you are to get caught by a trap, it just drops drastically. Even if there is a defect nearby, the electron basically ignores it,
It has blinders on.
in a way. The screening effect is reduced. The electron just shoots straight past the defect because it physically doesn't have the freedom to scatter sideways.
So by forcing the traffic into one lane, you stop the accidents.
That's a great way to put it. And because they aren't getting caught by defects, they aren't leaking out.
Which brings us to the device they actually built. We talked about 1T1C earlier, one transistor, one capacitor, the leaky bucket, and the tap. This paper proposes a 2TOC structure.
2 transistors, 0 capacitors.
0 capacitors. So There's no bucket.
No,
If there's no bucket, where do we put the data? I mean, where does the water go?
this is the wild part. The leakage is so incredibly low that they can use the transistor itself as the bucket, specifically the gate of the transistor.
I thought the gate was just the switch.
In silicon, it is, but every transistor has a tiny bit of what we call parasitic capacitance. Usually, it's just an annoying side effect. It's too small to hold charge for long, because remember, silicon leaks.
Right.
It's like trying to hold water in a thimble made of mesh.
It drains instantly.
Right.
Ah.
But with this MoS₂ aid contact, the seal is so tight that the thimble becomes watertight. The gate itself holds the charge.
So we don't need the bulky capacitor anymore. That must save a ton of space.
It saves space, but more importantly, it holds that charge for a very, very long time.
The retention time.
Yes. In standard DRAM, remember, we have to refresh every few milliseconds.
Yeah.
In this MoS₂ device, they measured retention of over 8,500 seconds
8,500 seconds. That's over 2 hours.
without a single refresh.
So if I'm watching The Fellowship of the Ring on my laptop, which is, what, 3 hours? My RAM would only need to refresh maybe once during the entire movie.
Theoretically, yes, compared to millions of times per second currently. And frankly, they stopped measuring at 8,500 seconds. The data suggests it could hold the charge for days.
That is insane. That's basically storage at that point.
That is why they call it quasi-non-volatile. It acts like flash memory, the stuff in your USB drive, but it works at the speed of RAM.
And there was one other stat that just blew my mind, the 5-bit memory.
Ah, yes. This is the density breakthrough.
Usually a memory cell is just 1 or 0, right? On or off.
Correct. But because this device leaks so little, you can be incredibly precise with how much charge you put in the gate. You're not just limited to full or empty. You can fill it 10% full, 20% full, 30% full.
Oh, like a dimmer switch instead of a light switch.
Exactly. They demonstrated 32 distinct levels of charge that could be reliably read.
32 levels. That's 5 bits per cell.
Yes. 2 to the power of 5 is 32. This means you can store 5 times as much data in the exact same footprint as a standard cell.
So let me get this straight. We have a chip that's atomically thin, doesn't need a capacitor, holds data for hours, and holds 5 times more data per cell. This sounds too good to be true. What's the catch? When can I buy this?
That is the million-dollar question. We have to be realistic about the lab-to-fab timeline.
Lab-to-fab,
This is a research paper. They built this in a very controlled environment, that custom vacuum chamber we talked about. Scaling that up to a factory that pumps out millions of chips a day is a massive logistical challenge.
Right. I mean, changing a semiconductor fabrication line costs billions of dollars. They aren't going to switch to MoS₂ overnight just because of one paper.
Exactly. The existing silicon industry has a lot of momentum, but the vacuum integration method they developed is a blueprint. It shows it can be done. It's not just theoretical physics anymore. It's an engineering process.
And the payout seems worth it. I mean, imagine the energy savings.
Well, it connects to the bigger picture of in-memory computing.
What does that mean exactly?
Right now, computers spend a lot of energy just moving data around. You pull data from the hard drive, send it to the RAM, then send it to the processor. It's a long commute for the electrons.
And nobody likes a commute.
It creates heat and it wastes time. If your RAM is non-volatile, if it can hold data like a hard drive, you don't need to move the data back and forth. You can do the processing right there where the memory lives.
So for AI or massive servers or even just my phone,
It could cut power consumption drastically. We're talking about devices that last days on a single charge, or data centers that don't require rivers of water to keep cool.
it really feels like we are at a turning point. We've been squeezing the last drops of performance out of silicon for years, but this feels like a new chapter.
It is the post-Moore era. The rules are changing. We're moving from 3D bulk materials to 1D and 2D physics.
And frankly, I'm ready for it. I'm ready for a laptop that doesn't panic when the power flickers.
A world without the capacitorless anxiety.
That's the dream. A huge thank you to the team at Fudan University, Gu, Zhu, Zhang, and the whole crew for showing us that the leaky bucket might finally get fixed.
It's really impressive work. It's exciting to see the physics of the very small solving the problems of the very big.
If you want to dive deeper into the charts and the Sommerfeld factor yourself, we'll link the Nature Materials paper in the show notes.
Definitely worth a read if you like your physics.
And if you enjoyed unpacking this with us, make sure to hit subscribe on the Deep Dive Lab. We're always hunting for the next big breakthrough.
Thanks for listening.
Before we go, I want to leave you with a thought. We've always drawn a hard line between memory, what we're thinking about right now, and storage, what we remember for later. But if this tech works, if RAM becomes permanent, does that line just disappear? Do we stop opening and saving files and just exist in a workspace that never forgets?
It certainly change how we interact with information.
Something to think about while you frantically save your work today. Thanks, everyone.
Goodbye.